Okay, hello. I'm joining in 1 minute before, I guess. Oh, well, it's on the hour anyway. Can you guys hear me? Oh, fantastic. Thank you. Thank you so much. There are only few of you actually today, so I wonder if we should wait maybe 2 minutes or so to see if the others will join before we start. Is that okay with everybody? Don't worry, we will not run over the hour anyway. So, okay, that's okay. Thank you, CJ. How's everyone? So let's just give it a few 2 minutes or so to see if more people will join. By the way, since you guys have arrived early, what I will do, let me share the URL to today's slide, but also the reference book, the book that I would recommend you to go through, which contains the Conjugate stuff, blah, blah, blah. I will make a comment after. So that way you don't have to wait until I upload them on GitHub. And the slide might change, obviously, if I spot any errors. Hopefully there are no errors. I cannot guarantee the same with typos. I always make typos, so especially when you have like 1 hour or so to do the slides and copying stuff, it's very easy to do, to make a mistake with LaTeX. So apologies in advance. And if you spot any errors, let me know. By the way, thank you, Aditya. Aditya spotted an error in the last session slide. By the way, I didn't have the chance to correct it, but it's a minor stuff. You will people will understand that it's a typo. Okay. So there are few more people joined in. So maybe let's wait another 1 minute or so before we start. Can you all see the slides, by the way? Oh, okay, cool. In fact, before we start, let me maximize it just to make sure the resolution. Is the resolution okay this way? Can you see the entire thing? Let me remove again and go back to the chat. Yes, okay. In fact, let me bring our friend Soham if on screen, if he's available. That will be cool. More people joining in. Okay, cool. Thank you so much again. Yeah, okay, so shall we start? I can see most of the regulars have joined in anyway. Anyway, you can make it clearer. So someone is asking. Not sure. Would that means like let me mitigate? Would that maximize help, or I mean minimize, or like this? Is this okay? Let me check. Maximize would help. Okay. 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 Let me refresh the browser just to see these things. Does it look any better? I don't think I've made any changes apart from refreshing. Check. Oh, the slide is stuck. Nothing's changed. Yeah, that's because I haven't changed it yet. In fact, let's see. Can you see any changes? The first one. I'm on the first page. Yeah. And now I'm going to change to the second page. Let's see. Okay. No changes. Okay. Maybe let me stop sharing and I start again. Sorry for that. Okay. I've stopped sharing. Sorry for that. Let me start again. Okay. In fact, I'm on the wrong slide. It's okay. I will use this one instead. What about this one? This is the Google Slides instead of the other one. Clear. Okay. Yeah. Okay. So let's use this one instead. That's why I have plan A, plan B. Can you see the transition? So I've gone back to the first page. Yeah. Okay. Good. Yeah. Sorry. Thank you for your patience and sorry for that. In that case, we'll use Google Slides. Okay. Yeah. So welcome to session 11. So today's agenda is, again, I decided to split it in two parts. So the first part is to, the lecture comments and then go through these things. The reason I do that is because I want to avoid a situation where I define these things in here and then, it might be confusing to you that these concepts are only defined for elements of matrix groups. So this is general concept. This stuff here don't need to be elements of a matrix group. So I hope this will make it a little bit more clear than mixing it. So on this part B, we'll just get into group theoretic stuff. Okay. In terms of this month's agenda, so we are here. Next week, there will be one session. And the week after, on the 18th, is the last session for this year because 25th of December, I didn't even realize that until I looked at it a few days ago, happens to be on a Friday. So I'm not sure if any of you, would be bothered to be, being hammered about Hilbert spaces and this thing on a Christmas Day. So yeah, so I hope it's okay with you that we will make a break. And on that week, on the 15th, we will have a fireside chat. I will comment on that at the end. And then New Year's Eve. So this is the thing. The 1st of January happens to be on a Friday too. So I'm not sure with at least with myself, with the hangover or whatever, if I will be in a position to. Yeah, okay, yeah. George is saying maybe we could have a Hilbert space for Christmas and Bana. Yeah, that sounds good. We can have Bana New Year's Eve, Bana hangover, So I think you all agree that, we should probably not have any session on this week, on this thing. So we'll have 2 weeks break, essentially. This brings us to January. So the first session will be on January the 8th, then the 15th, and then hopefully January the 22nd will be the last session of this module. I will comment more on that once we get near about what next, about the next module. It's looking more like maybe it will be in the summer or sometime, maybe even more or less the same start. We'll see anyway. So yeah, going back to the foundation module, well done to all of you, especially the ones online at the moment. As you can see, we are here. You will also realize I've renamed this section to Matrix Groups 101. I think this is probably the more fair description than just leaving it Matrix Groups, because Matrix Groups without talking about Lie groups is really like a little bit strange. And we cannot talk about Lie groups without talking about manifolds and all these stuff, which we will not do on this module. We'll only do that in the next module. So yeah, so I've renamed it Matrix Groups 101, and we'll focus on these groups today. And it won't be the end of it. This is just this is just a taste of it, and then they will appear again. They will appear in here. They will appear again in here So it won't be the end of groups, or at least their elements, the elements of these groups. Okay. Let me check the chat before we dive in. Yeah. There's no question. I hope you're still with me. Okay. Sorry for that. Okay, so another thing I want to comment here is we are now getting to a stage where you will see more of this thing here. You know, when we started, I was saying, you know, we'll have this thing where we'll go abstraction, concreteness, and then give you a quantum hint. By that, we mean, you know, give you a hint on how the mathematical stuff, concepts that, you know, you are being exposed to are being deployed in physics. But don't confuse this. This will not be, unfortunately, this will not be, we won't dive deep into the physics of the things, really, because this is a mathematics stuff. I'm a pure mathematician, not a physicist. So, but hopefully I will give you enough taste, hints that, you know, will kind of get you a bit of insights into how the mathematics is being deployed, and hopefully get you interested, and, you know, for you to go and dig deeper. Ultimately, you are it will be your responsibility to try to bridge the gap between the mathematics and the physics, really. Okay. So let's go to part A. The first definition is that of a matrix conjugate. Okay, so if you have a matrix A, in this case we are starting with 2 by 2 matrices, but this can also be generalized. So the conjugate is nothing more than just the conjugate of the entries. For those of you, if you remember, on the GitHub, we have a book called pre-course thing, or whatever I called it. It has a thing about complex numbers. So I expect you to know this. I'm sure you will know, even if you, for those on YouTube also. So given a complex number, the conjugate of the complex number is this thing here, okay? One thing that's very important for you to know is this convention stuff. Mathematicians, especially if you, that's where you have to be pay attention on what, you know, who writes the book that you are picking. If it's a physicist or mathematician, mathematicians normally for conjugate they would write the bar on top of the element. Okay, so that means we would write. They would also extend this to the matrix itself. So they would write this instead of star. But because, you know, this thing is about quantum formalism and these things, I decided to follow the physicist convention, okay? But it's very important that you notice the difference in case you pick a book written by a mathematician who doesn't care about physics. You will probably see a different notation, okay? And here's an example of, you know, I hope I got it right. So, you know, you can see the conjugate of this. You can notice something very special, which is a property of the conjugation for complex numbers, is that the conjugate of real numbers don't change, right? Conjugation only changes the complex part. So in this case, the only thing on these matrices that changes is this one here, right? It flips the sign on the complex part. We are clear on that, right? Yeah, okay, cool, thank you. So the next definition, let's go, is that of a conjugate transpose. So you have the conjugate matrix. So all you do is to take the transpose of that. So you transpose, it doesn't matter how you do, which order you do it. You can also transpose and then take the conjugate of the entries, or you take the conjugate of the entries and then you transpose. It doesn't matter, but that's the definition. So I hope this is also clear. And physicists write, to denote the conjugate transpose, physicists write this thing here called the dagger. So they call this a dagger. And the confusion also is that mathematicians write star instead. So be aware, if you pick a book on matrices and the mathematician writes this, it means the dagger for the physicists, okay? And obviously the definition can be extended to not just 2x2 matrices, but also to n-by-n matrices, okay? And just as a curiosity, we'll come back to this in the next few sessions or so. So A is Hermitian if it's equals to its A dagger. So to its dagger, I mean. So that's the definition of Hermitian matrix. From the previous examples, you can see it's clear. You will be able to see which ones are Hermitians. And then the next thing that as a homework for you, and I have quite a lot of homework for you on this. You can see these properties. So the claim is that these properties hold the conjugate of A, conjugate of that, the conjugate of the conjugate takes you back to the original matrix and all this. Okay. So this is notice this also here. This is very interesting because it says the conjugate of the product equals the product, but inverted. The elements are inverted. The order of the product. Okay. And then this nice property here, the determinant of the conjugate matrix is the same as taking the determinant of the matrix, which is a complex number, and then taking the conjugate of that. And then another property is that if A is invertible, then A dagger is also invertible. You will be able to prove this, especially because we are talking about toy stuff. You can do manual calculations. I trust you will be able to prove this. This can also be generalized. Okay, let me check the chat. Is that typo on 2? Let's see. Lambda. Oh, you mean this? Yeah, there is a there is a typo here, I believe. Yeah, in fact, this is as a homework actually. Double check whether this is a typo or I forgot to add the dagger here. Yeah. You think I forgot to add the dagger? Yeah, you can debate on that if this is a typo, whether I forgot or this is actually indeed this is the thing. We don't need a dagger on this side. I'll leave it as an exercise actually. Okay, so I hope there is no confusion here on this. It's just what you need to pay attention on is the notation stuff. You know, if you are giving the thing, if you see a mathematician, so just look at the book. If it's a mathematician who wrote the book, then you will know that you have to pay attention in the thing. If it's a physicist or mathematical physicist, they normally stick with this convention. Okay. I think I already said this. This also, all this thing applies to this. Okay. So before I move on to part B, let me check. How do much between, well, mathematicians, let's see. Remember, this goes back. This is consequence of this, right? So this is the thing. This is the conjugate for a mathematician is this. They will write this and they will write this in here, okay? And then for them, the star will be the conjugate. So it would be a conjugate of the bar here for a mathematician, if that's clear. Yeah, it's okay. It's very easy to make confusion with the notation. This is where there's a kind of subtlety in the notational side between mathematicians and physicists. But you won't have that problem. This is where it's very important for you guys, as you get into these things, to be able to see how notations different disciplines, the way they do things. Okay, so let's go to part B, which is the important part. The first thing, I'm going to start with the circle group. It's first of all, you remember this, the C star, which is the set of all non-zero complex numbers, and we have seen this from the previous section that this is a multiplicative group, right? It's a group under multiplication, okay? And now we can define this set, okay? This set is U1, we call it, is an element of a lambda, element of C star, such that the modulus of the absolute value of lambda equals 1. This is where you have to revisit if you don't remember what this means on the thing. You have to go back to the complex number stuff, what this means. So this essentially, this is you can see here. Can you see, by the way, it's a little bit small for me, but this is essentially the unit circle on the thing, on the complex plane, really. So the element, the points on the circle can be identified as the group element, okay? Sorry. I think we'll have a problem with this because you cannot see when I hover the thing. Let's see if I can fix this. Maybe a little bit, yeah. Can you see now? Actually, can you see the this bottom part when I hover the mouse over it? Yeah, okay, yeah. So essentially this U1 is, can be viewed as, the unit circle on the thing, and so the points are the elements of the group, and they have this form, and the multiplication works like this, is the same e to the I, and then you sum through the angles, you don't have to worry about this thing. Let's stick to the algebraic stuff. These are things that will show up more once we get into Hilbert spaces and these things, and maybe even when we talk about Lie groups and these things. For now, let's just stick to the algebraic aspect of it. I just added this, so I know some of you maybe might find this very interesting. So you can also play around with it, okay? Okay. And you can see, obviously, U1 forms a subgroup of C star. If you cannot see this right now, I think if you, at home, if you go through it again, you should be able to conclude that U1 is a subgroup of C star, okay? And now, here's a hint. This is just a hint. I'm not going to dive too much into it. It's one of the hints. So U1 is indeed an example it's the simplest example you can find of a Lie group. So in the advanced module, you will know what a Lie group is once we, go through the manifolds and all this stuff. But U1 is also a very important group in theoretical physics. Theoretical physics. This is what the physicists call gauge symmetry. For example, in quantum the reason why quantum electrodynamics, for those of you who are fans of Richard Feynman, he's the godfather of this field. The reason why this field is what they call a abelian gauge theory is because the symmetry of the theory is U1, okay? And as you know, U1 is obviously, as we've seen before in the previous slide, is a abelian group, okay? And it's also a very important thing in the in the standard model. You will see that in the next slides. It's an important piece of the standard model of particle physics also, because it features in the gauge symmetry of the standard model. For those interested in quantum hardware also, I made this note. I'm not that sure, but I believe the QED is the foundational thing for this cavity quantum electrodynamics, which I think some people are trying to exploit to build quantum computers. I'm not really sure, but you can search this. And there's also something called circuit quantum electrodynamics, blah, blah, blah. But yeah, so that's it. I won't dive into it because I would probably not be not qualified to talk to you about what these guys are up to. But hopefully it gives you enough hint on the importance of of U1. So let me check. Yeah. Yes. So Aditya is saying, is this about the context of standard? Yes. Yeah, we will get there on the other slide. So you're yeah. Okay. So thank you, Soham. Actually, by the way, sorry for answering on the chat. So now we can define the unitary. Well, it's not a group yet because we didn't, but yeah, let's define this set. Let's call it U2. So it's a set of all matrices in GL2 that have this interesting property. So A times A dagger equals A dagger times A equals I. So in other words, the inverse of A is the dagger. This is very interesting. So you can see the example. These are some of the elements of U2 that satisfy these elements. You know, some of you already coming, those who taken courses in quantum computing, or the guys coming from physics and are being exposed to spin 1/2 thing will know this. But nevertheless, for those watching on YouTube and the ones who are not, these are like typical prototype. I mean, you can just do the exercise, go back again on the definition of A dagger, and you will be able to see that these matrices are indeed elements of U2. This can also be generalized, which is why I did, to this. So for UN, for any n greater than 1. By the way, some of you already figured out that U1, instead of defining it the way I did in the circle group, blah, blah, that could also be defined as a set of 1-by-1 matrices, right? But yeah, so for any n, you have this, okay? So the elements of UN are called unitary matrices or unitary operators. You call them operators when they are acting on a vector space, which you will see in the next few sessions or so, on a Hilbert space. CN will be a Hilbert space. And I guess this is now trivial, right? U2 or UN in general forms a group, right? Who disagrees? No one disagrees. Perfect. Does anyone have any doubts on? Well, if you have doubts, I have the next proposition for you as a homework. Is that U2 is a group of GL2, okay? And this is also valid for any n greater than 1. So UN is a subgroup of GLN, okay? And this is very important also, I would say. This maybe I should have called quantum hint, is that when you are dealing with the quantum computing, you probably want n to be equals 2 to the k, where k is the number of qubits, so that the UN or u to the 2k acts on the Hilbert space, which is this one. Well, it's not yet a Hilbert space, but you will see in the next few lectures, this is a prototype of a Hilbert space. So even though the unitary group is very interesting for any for n, in practice, you kind of discriminate what sort of n you want. You want n to be equals to 2 to the k, okay? Yeah, and this is some interesting properties that we will see later about UN on the thing on acting on state vectors. Some of you already on the class, I know, already know this, that the unitary operators, for example, preserve the norm, blah blah blah. But we'll get to that, okay? And there's also some relationship that we will explore in the next coming session between unitary operators and Hermitian operators, okay? But that's in the future. Okay, so let me check the chat. Okay, so Amir is asking, is it not always the case that we define unit, this set of elements? Yes, we define, so U2, let me go back to the slide so we are on the same page. Yeah, so I define it this way as, because what we want is, we know that U2 is well, I know that because it's I know it's a subgroup. So what we want is obviously GL2 is a group, And in practice, if you remember last time, I was saying it's the group is too big to be very detained. So in practice, what you tend to do is to work with its subgroups, okay? Because it's too big. Unless you are a mathematician, doing things like algebraic geometry and all these stuff. Maybe it will be projective geometries, all these things. Maybe the scope of your universe will be can be a little bit bigger. But for physics and other things, you actually in practice you want the subgroups, and you will see actually even for U2 or UN in general, you actually also want a subgroup of that. Okay. Let's see actually if does that answer? Yeah, okay, cool. And obviously, this is deliberately, the definition here on this thing. But in general, if you were looking at this just on the set theoretic thing, you could define a subset of these that could maybe, but on their own, might not form a subgroup. So not any subset of this can class as a subgroup. Okay. So I don't know if that adds to the confusion or adds to the clarity. So, yeah, so Aditya is exactly on the chat. Yeah, for a subset of a group to form a subgroup of the bigger group, it has to satisfy that. It has to be a group under the same operation, or there is a shortcut. If you go back to the previous session, if you recall, there is I think 3 conditions for a subset to be a subgroup of a bigger group. Okay. Okay. Let's go back. Now, here's an interesting proposition. In the last session, we talked about centers. Let's now look at the center of U2. So the claim is the center of U2 is of this form. And now I also have an interesting challenge for you, is for you guys, especially those who are interested in quantum computing, and there will be more actually at the end of the session, to try to think which qubits are at the center of this. Are there any? So you don't have to answer now. Obviously, you can go food for thought. And the same, this definition can be generalized. So the center for UN equals has this form, where IN in this case is the identity matrix. And another question is, if it's not obvious to look at that, whether the center of UN is isomorphic to U1. Who thinks yes? This is easy to see. Or you need a bit of thinking. Yes? Does anyone see why is true? The thing you can build. Remember, being isomorphic means you can build a homomorphism, a homomorphism that's bijective homomorphism, right? And you can see it's true. You can take F, so you can go from C2, from the center. Just imagine a function F. So F of this matrix would be just equals to lambda, right? And because the lambdas are unique, therefore you have an isomorphism between the center and U1. Okay, yes. So Aditya has expanded on the comment. I can see there. So yeah, if you are having the thing, just I'm sure if you think if you are one of you're not seeing this, why this is the case, just at home, just go through it and think it through. I'm sure you will come to the same conclusion. Okay. And there's another proposition, a very interesting one also, that says, remember, the determinant is a homomorphism. So, well, actually, I don't think we said that in the previous when we talk about general linear group. Yeah. So anyway, the determinant from U from U2 to C star is a group homomorphism. And very interestingly, I also claim that the kernel, remember what the kernel is? If you don't remember, go back again to the previous session. The kernel is, well, I could have said equal, but I will just say contained on this special linear group. Remember what the special linear group is? Again, if you don't remember, just go back to the slide, okay? And this can also be generalized to, to UN, okay? So let me go back. So before I go, I think we are all on the same page. Does anyone have any doubts, any question? Feel free. Don't feel intimidated to ask. It doesn't matter, the thing. But I also recommend you, because it's very hard to come, the thing, especially if you are new to these things, it might take you sometimes some thing to digest and be able to see this type of stuff. That's why I encourage you, as you have noticed, over the last few sessions, in the last, I think, I don't remember when I actually, myself, I've given you an example of a proof. I've been just saying, try to prove this, because at the end of the day, you need to feel comfortable to prove stuff. And if you get stuck with something or whatever, you need my help with these things. I'm happy to help. There will be some occasion, especially in advanced stuff, that I will present a proof, so you can, because it's those stuff are harder in my point of view. So I will do that. But another thing I want to say is that when you come up with a proof, don't feel don't feel bad that your proof is different from someone else's. Yeah. So don't discount your. It's not that you are wrong, because there are several ways of proving things. So there isn't one way of proving things. So don't feel discouraged if you in whatever home challenge I give you to prove something. Your line of argumentation to get to the proof is different than what you see on the test book or elsewhere. Okay. So obviously, some proofs are nicer than others, or as people say, some proofs are more elegant than others. But yeah, never feel discouraged just because your proof is different than the other. It doesn't mean you are wrong. It's just you use you arrive there at by different using different thoughts, your different argumentation. So okay, so let me go back. Go forward. Now we go to the special unitary group. In this case, SU2, because we are dealing with 2x2 matrices as our toy model. So it's a set of all elements in U2 with determinant equals 1. So the ones that have the determinant 1, okay? This can also be generalized to any n like that. So SUN equals the matrices in UN that have determinant 1, okay? And I hope this also, if you cannot see this, this is also easy, that SU is an intersection between SLN and CN, sorry, SLN and CN. UN and SLN. Yeah, I always struggle with pronouncing stuff. Okay. And the claim is also that SU is a subgroup of U2. Sorry, SU2 is a subgroup of U2, okay? And this can also be generalized to SUN, which is a subgroup of UN also, okay? Let me go back to the chat. Yes, so Ham is right. Elegant proof comes with the practice. If you do a lot of practice, yes, like George is also saying about music, it's all the thing, it's like practicing anything, even in sports, the more you do this practice, the more you become sharper in doing things. So, or like those of you, the programmers on the audience, the more you program, the better you become a better programmer, right? So it's the same thing. Okay, so thus far, there is no questions about the definition above, right? Nobody you all happy with the SU, and you can see that it's also a subgroup. Okay. Okay. So I promise we are not far from the end. So here's an interesting proposition: is that the center, an interesting claim, the center of SU2 is of this form. Okay, and the question, first of all, this is a homework challenge. So the claim is that the center of SU2 is of this form. The second challenge I would, in respect to this, is which gates are in the center of SU2. You can go and check all the gates. By which gates? I mean the ones that you find in textbooks, or find in the documentations of whatever, whether Qiskit or whatever quantum hardware stuff that they support and these things. So go through that the list and see which of them. And this can also be generalized. And the claim is that the center of SUN equals this. This is very interesting, right? I think this already showed up in the previous. I think it was Soham who gave an answer for when we talk about the center of SLN. Let me check the chat. Okay, and here's a proposition. It says that the determinant of this is also that. You can check that, blah, blah, blah. And something here that I want to encourage you also is, even though we are working with the SU2, SU4 is also very interesting, because it's the thing that deals with the 2-qubit gates systems, right? So go through the 2-qubit gates and see which of them, the ones that are part of SU4. SU4 is obviously, you go through the definitions of in here, right? Is the set of elements in U4 that have determinant 1. So I encourage you to do it, because this is how you see the thing. Because so far, most of the stuff that I would say, like the way you were exposed to the quantum gates will probably be like not in this structural thing. Now you kind of see them like I think you are now seeing them differently. You're seeing them as elements of a bigger universe, interesting universe out there. Okay, so it's not just these rules that I see in some courses they put in. Oh yeah, you do. It's you do this, you do that. That's a unitary, and this is the thing. You are now seeing the gates, as part of us. There's an order. There's a structure. They are part of a very interesting universe. They have a very interesting algebraic structure. And we are not even we are just at the tip of the iceberg, because when you add in the Lie groups structure into it, I mean they are Lie groups, even under the hood they are Lie groups, but we are not exploring the Lie properties in a rigorous fashion, or in an explicit fashion. But you already see that they are very interesting. So I hope that's one of the takeaways of this module, is that some of the stuff that you were seeing, like individual trees with some properties, and they are actually part of a bigger forest. That's I guess that's probably the best way to put it. Okay, so let me check the chat. Since you mentioned Lie, can you briefly describe what that means? Well, that's the thing. It's very hard to talk about Lie groups, because we need manifolds, because it's okay. In a simple terms, it's a group that's also a topological manifold. Yeah. Now, if you ask me what's a topological manifold, I have to go again. Okay, a manifold is he's a topological space and blah blah blah. So we don't have the language yet for us to to talk about this. But I promise, if you come to the advanced module, when we start with the basics of topology, you will know what a topological space is and so on. We will get to topological manifolds, and so on. And then it will make more sense to talk about Lie groups. Okay, but they are very important. Yes, the group operation is continuous. Yeah, so yeah. So George is and Soham are saying, yeah. But for most of you on the audience that are not coming from advanced background, it's probably, it will just add to confusion, because any word I say, I have to define it, and then it's keep going. Yeah, but be patient. You will get to that once we get to the section dedicated to Lie groups. And actually, it's not just, this is the thing with this quantum stuff, it's not just the Lie groups themselves, because for a Lie group, you also have something called Lie algebra of that group, okay? So for SU2, you have small SU2, okay? I won't say more anymore. I will just stop here to not confuse you, okay? And it's very important, actually. I'll just add this extra note, especially for advanced students, that often in physics books, sometimes physicists, they confuse, like, it's a bit confusing to know when they are talking about the Lie group or when they are talking about the actual Lie algebra of that group, okay? So, yeah, anyway, it doesn't matter. Let's just leave it there, because I don't want to go too much into it. We don't have the tooling, the language to be able to discuss this. Okay, and this is another quantum hint I would like to share with you, and I highly recommend that you ask a particle physicist to see whether what I have here is true. But yeah, so SUN is a very important ingredient of what physicists call gauge theory, gauge theories, So a standard model, for example, is the Bible of particle physics, which is the standard module, is a non-abelian gauge theory, because its gauge group is made of these components, these terms here, these other groups. What this means, we will also touch this in the Lie groups section when we talk about them. Okay, so essentially, the first one, which is SU3, you know what SU3 is. Let's take it from just algebraic, from what you learn from SU3, is responsible for what they call, quark color changes. So the quarks, they have these intrinsic properties that they label, physicists label them. This is not color, it's not like they have a color, this is just labeling that they call green, blue, blah, 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 which is essentially responsible for the strong nuclear force. Okay, and then you have SU2, which is responsible for the weak nuclear force, and then you already seen this. This is responsible for quantum electrodynamics, or this is essentially this is the quantum version of the electromagnetism. I think Soham and the other physicists on this will probably be able to correct me on this. Okay, and here's a very interesting question: is what about gravity? Why is not gravity included in the standard module? Okay, this is an open problem that a standard module does not at the moment does not include gravity. So that's why when you hear physicists say the standard model is incomplete, is because it's not included in the description of the standard model. It's an open problem. So maybe you will, some of you on the audience will go and come up with a theory. There are so many other theories to candidates for this, string theories and all these other stuff that try to loop quantum gravity, that try to include a quantum description of gravity. But it's an open problem, okay? And it's not something, as I said, this is just a hint, hopefully to encourage you, some of you, to see that groups play a very important role in nature, even though they are like a very abstract mathematical thing. This is just to show you, that they are very important. And this is by chance, actually. It happens to be this. It's not like, okay, yeah, nature happens to choose these groups to describe it. This is what the beauty of the thing. So, yeah, I think I'll leave it here. I won't make any further comment. I don't know if Soham can have anything. Yeah, I see Soham already adding some stuff about quantum gravity. Yeah. So, yeah. So maybe actually one of the things that I will do is in the next module, I might invite some theoretical or mathematical physicists to do like a fireside chat with you. But I want to do that once you have the mathematical machinery to be able to understand what they are saying, right? At the moment, it's too premature to do that. But in the advanced module, this is one of the things that I want to do, is to have like a fireside chat or some sort of technical webinar after you have gone through the hard maths, because then you are able to understand them. Okay. So we leave it here, and apologies to the particle physicist. Watching this, if I got it wrong, apologies. It's a pure mathematician here trying to do something, trying to teach physics. Okay, so on that, I would recommend you these books. They don't really have mathematics on them, really, hardly. It's just few basic stuff, but it's very important. This one written by Feynman himself. So it's called The Strange Theory of Light and Matter. And then there's this one, Quark and the Jaguar, blah, blah, blah. And then you have Steve Weinberg. Very, very good books. I've read them, but maybe honest to say that I've skimmed through them. And there's actually a funny story with that. The reason why so I had a friend of mine who was a theoretical physicist. He's no longer with us. He passed away. But he came to me like a few years ago in the student times, saying that he needed my help because he was thinking he has some ideas related to spontaneous symmetry breaking. I was like, whoa, man, I don't think I can help you with that. That's very, it sounds very complicated, spontaneous symmetry breaking. All these jargons, scary stuff that throws you out. And then he was like, no, actually, I need your help on the group side of things, So I was like, okay, I will think. And then I was a bit reluctant in this thing. And then to bribe me, he gave me these things, so I can have some basic understanding on the thing. So when we are going through the group theoretic stuff, he can group theoretic, not just a group on the sense that we're doing, but there's also something called representation theory. I won't mention that, but yeah. But they're really good books anyway. Long story short, I'd really encourage you before you kind of because they give you intuition, especially Feynman. Feynman is very he was brilliant in terms of physical intuition stuff. He invented these Feynman diagrams and these things. So I really recommend you, if you have time, to go through this. Okay. Yes, it's true. Physicists love to use jargon. So that's why I would actually say to you, if you hear a jargon, don't be scared. All these terms, like I was saying, spontaneous symmetry breaking. You will, whoa, what's that? It's like it's very complicated and all of that. It turns out I didn't need to know much about all the stuff. I just needed to understand a bit what he wanted with the group on the group theoretic and representation theory side. But I was like, whoa, that's too. Yeah. Anyway, so I encourage you really to these books. Anyway, yeah. I mean, some of you want to follow physics. You never know. Maybe particle physics could be a path for you. As you see, there is an interesting open problem. You never know. Maybe one of you will solve this or help solve it. Okay, I'll be very happy. Don't forget to invite me in your Nobel Prize award ceremony or whatever. Okay, so let's go back to the materials. This time I've done something a little bit different. Rather than giving you a maths book, because we are getting into quantum stuff, next week or the week after. We're already in the quantum stuff. And because we've talked about groups, and the quantum gates are elements of those groups, yeah, so I thought it's kind of probably better for you to go and play with the quantum gates. I found this, I found this as a thing. I have a copy of this, of these pages, so you don't have to buy it. And I think there was a link. Let me share the link again for those of you right now watching the, in fact, I will share this slide. I've shared it before, just before the lecture, but because the chat has taken everything, I will reshare again. Okay, so it seems Cloudcast is very, very clever. It's telling me that I've already sent this message. So let me change a bit. I've misspelled stuff to see if I can click Cloudcast in order to share the link again. Yeah, okay, so it's the second slide. I mean, the second resource link. That's what contains this. So go through the quantum gates, and see which ones are elements of SU2 and blah, 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 and all this, play around with them, because now they are part of a, of the group universe, okay? So they are elements of a group, okay? So, maybe you'll find some interesting stuff about them. That's the whole purpose of this module, is to give you this thing that, enable you to see the things differently. The stuff that you were, all these gates that you were playing around with, maybe I would say a lot of you, apart from those coming from, advanced background like Sohams and these things, you probably didn't, see the gates as, being part of this very interesting universe, So I hope you will enjoy. And you can also, it doesn't have to be this, it could be also the other one from, Nielsen and Chuang or something, go through the thing and play around and see which ones are are part of SU2, SU4, so, or SU8 also, which is also relevant. So if you are SU8 for 3 qubit, and so on. So, okay. Another thing, I know we are, I promise we're going to end in a minute. The fireside chat. So on the 15th of this month, so in about 2 weeks' time or so, at the same time as the sessions, okay? You can see I've corrected this. It was 10:05. It was meant to be 5 o'clock, right on the hour, but don't worry. And for this, I've actually nominated our friends, Amir. Okay, so let me just, before that, Nicholas is asking, why are the SU so important? Are there underlying reasons? Yes, they are important. As you can see, for example, yeah, okay, so Soham is answering, that's fine. Yes, exactly, that's right. So nature seems to like them, because a lot of the symmetries that describe nature happens to be in the thing. So it's not like the mathematicians chose the thing, is like nature, because physics at the end of the day is an experimental thing, right? If, there's no, a mathematics, a theory can be beautiful in mathematical thing, but if, there's no evidence that nature, actually, the mathematics describes nature, then it's like a worthless, right? But in this case of SUN, nature happens to like them, as you can see in some of the, like SU3, SU2, and so on, okay? Symmetry is just, so when you hear a physicist say symmetry, just think group, okay? Something that preserves, so in the case, let me give you a nutshell thing. This is, again, I was trying to not get into physics. For example, something that, for example, imagine the equations of motion, for example, a symmetry would, for example, preserve the equations, it's probably better to share some resources on the chat where you can explore this, because I don't want to make this into a physics class. But just think of a symmetry as when you hear the word symmetry, think about group. Okay, that's the abstract. Group is okay. So there's an example that George is given, for instance. Yeah. So the group theory is the language. You can see that is the language that describes the thing. So when a physicist say, this, the symmetry group, blah blah blah, or symmetry, this, just think because the groups are they have the property that enable you to express the concept of symmetry in nature. They encode that. Yeah. Yeah, so thank you, Soham. You mentioned the Lagrangian. I didn't want to mention this because then people will ask, what's the Lagrangian? So the equation of mode, yeah. So yeah, there you go. Maybe this is something that we go through it's probably easier to do that on the Gitter chat. So we don't dive. I didn't want to mention Lagrangian because then you go, oh, okay, Lagrangian, what's Lagrangian and these things, and then people will say, what about the Hamiltonian and so on. Yeah, the Hamiltonian will deal with that in the quantum stuff, but yeah. Anyway, so we'll have. Let me go back again to here. Sorry for that. For those who are staying, the thing I was a bit off track. So I've nominated, self-nominated our friends Amir and maybe Aditya, if you want to take part. To moderate, so you do like Sohan did with the other fireside chat. Yeah, so there's also, just before I go back, actually there's a book called Symmetries by Hermann Weyl, group theory. Okay, so Aditya, going back to the thing. So Aditya is saying I might not be able to make it. That's fine. What about you, Amir, on the 15th? That's fine. If you are not able, that's fine. Aditya, I mean. The reason I'm choosing, especially Amir, is because of this is a game. So if you go to the page, I will share you the page. They have a trailer about his company, Quark Interactive. They made they are an educational quantum company where, you play around. So you do the circuit stuff by playing around, So, okay, so in that case, we just, I've nominated, in that case, Amir will be the moderator. All you do, Amir, is to show up, like maybe 10 minutes before, so we can test the setup and these things before it goes alive. And essentially it will be, I don't think Lau will do any presentation like Amira did in the previous fireside chat. So it will be more of a kind of a dialogue type of stuff where you can ask whatever questions that you have, and also whatever questions that the others have. Okay. Okay, so that's it, really. And for those watching on YouTube, again, I'm not sure even if this is worth mentioning because you already know about all this. So maybe I will stop. I'll stop here. If there is no other question, is there any other question?
Yeah, I think there was one question which I missed. What is the relevance of the determinant of a matrix in the context of quantum gates?
The relevance of the determinant?
Yes.
Well, in our case, in the group theoretic sense here, as we've seen in the previous lecture, it's the concept that enables us to decide, whether something is, is a matrix. In this case, is invertible, right? So in the case of the quantum gates, for example, they are unitary. It means they are invertible. So it means their determinant is non-zero.
Right. So it will be for reversible quantum computing. You need to have unitary,
so obviously
unitary
to do reversibility, you need that's why they are chosen.
Right.
Right.
Yeah, I think that was pretty much all the questions that we have had today.
Okay. Was there any other thing?
No, I don't think so. I had a question for you. Are you going to talk about like? Are you going to talk about the representations of groups in the next module or something? Like
Yes.
group. Okay.
So this is why I called this group matrix groups 101. So
Right.
in the next session we'll dive more in the next module. I mean, we will dive more. For actually. Especially when we deal with in the functional analysis section, where we deal with infinite dimensional vector spaces. So we'll work with groups in a much more abstract settings, really, than
Right.
what we've been here. In this case, obviously, we are focused on finite dimensional vector spaces. But yeah, groups will show up again and again and again, and then we'll have a dedicated sections about Lie groups and Lie algebras plus the representation. So there will be representation also. I didn't want to mention this because people will ask what's the representation, but we'll also have like the concept of representation theory, which also plays a very important role in particle physics, because it's not just about the group theoretic concept that we cover here. There's there's a lot of representation theory there. Okay.
Right.
So Nicholas is saying, thank you, difficult. Okay, so it was a difficult session. Was this, so Nicholas, you are saying, is this session or this is like a general commentary about the entire, oh, this one, yeah. Well, it's a hard, it wasn't easy, but I think if you like take few days, this is why it's very important for you to refresh again, go through it, take your time, go through it and write the stuff, go through the stuff and do some practice. That's how these things get into your head, really, because otherwise it's like it's hard. Ignore the physics. This is one of the reasons why I kind of I was like in danger of making this into physics. That's why I'm very kind of reluctant to talk about physics. That's why I put it quantum hint. This is not the thing. So ignore the physics side. You don't need to know that. This is a mathematics thing. And then as you study the physics itself, you already the purpose is that to give you the mathematics. So if you decide to go and study physics later, you are not at least struggling with the mathematical concept that appear there. So that's the purpose of this. Yeah, I'm not a physicist. That's why I don't feel comfortable even talking about physics. But yeah, the purpose is that I will give you enough thing on the mathematical side, and then as you learn the physics, you will be bridging the gap between the two. Okay, so yeah, and maybe you will. The purpose of this side is actually to make it to try to be as rigorous as possible. Because from my point of view, a lot of times, if you think the physicists tend, because obviously physicists, they don't, which is right, because they don't have to worry about rigor and all these this stuff. So they tend to be all over the thing place. But yeah, hopefully the approach we will take, which is maybe a little bit more axiomatic, make it easier for you to organize your learning experience, to make it easier for you to learn. So I'm a little bit inspired by Bourbaki, actually. So I think you probably already noticed that, but in the pedagogical sense. So yeah, I don't have anything else to add. So thank you so much. And Soham, again, thank you. It was a very interesting session. I try to stay away from physics. So physicists watching this, I don't feel offended. Okay, so I'll see you next week. We will really start with with the Hilbert space section and all these things. So there's more to come. So yeah, so have a good weekend, everyone, and we catch up next week. Okay, thank you, and Soham again. Thank you.
Yep.
Thank you, everyone.
Thanks. Bye.
Okay, I see you. Bye.